Well, good afternoon. My name is Dwayne Brown with the Office of Communications here at NASA headquarters. Today, you will hear firsthand new discoveries and a few surprises of planet Mercury revealed by NASA's Messenger spacecraft. And on March 18th of this year, it became the first spacecraft ever to achieve orbit around this mysterious celestial body. We'll have brief presentations from our participants, a little surprise before we open up the Q&A, and then we will go to the website where you can look at the various images and findings at www.nasa.gov/messenger. Let me introduce you to today's participants. First up, Brett W. DeNevy, scientist, Johns Hopkins University Applied Physics Laboratory, otherwise known as APL, in Lowell, Maryland. Larry R. Nittler, scientist, Department of Terrestrial Magnetism, Carnegie Institution of Washington. Sean C. Solomon, messenger, principal investigator from the Carnegie Institution also. And Ralph L. McNutt, Jr., messenger project scientist, also from APL. Before we start with the official presentations, it's my honor and privilege to turn over to Sean for some opening remarks. Sean?
Thank you, Dwayne. We're delighted to be here today to share some of the findings from the first 25% of our year-long mission, Messenger, in orbit around one of our nearest planetary neighbors, yet a planet that has never had an orbiting spacecraft before Messenger. I wanted to begin by telling you that we passed some substantial milestones just earlier this week in our mission. On Sunday, we had the first perihelion passage, closest approach to the sun since we've been in orbit. On Monday, we logged in 1 Mercury year in orbit. On Tuesday, we came out of a solar conjunction when the sun was in between Earth and the spacecraft, allowing us to communicate again after being blocked. And just yesterday, we had the first orbit correction maneuver in orbit that lowered our closest approach to the planet back down to 200 kilometers or 120 miles. On most days since we've been in orbit, we have received new data about this planetary neighbor of ours almost nonstop. New images, new data from all of our 7 instruments. We had many ideas about Mercury that were incomplete, ill-formed, that came out of the few flybys, the 3 flybys by Messenger and the 3 flybys in the 1970s by the first spacecraft to visit Mercury, Mariner 10. Many of those ideas are now having to be cast aside as we see orbital data for the first time. We are confirming a few of the theories that have preceded us, but many of those theories are now being cast into the dustbin of science as they are shown to be a very incomplete or incorrect description of the innermost planet. You'll hear examples of those from each of the presenters today. One of our instruments on the spacecraft is, of course, our imaging system. We've taken more than 20,000 images of Mercury to date, and I'd like to turn the microphone over to my colleague, Brett DeNevy, who will describe some of the things we're learning from those images. Brett?
Thank you, Sean. Well, it's my privilege today to share some of our early science results from the Orbital imaging campaign. If we can pull up the first image. This is a view of Mercury looking down on the North Pole. And this is an area that we didn't really have great coverage of before due to the nature of flybys. So you can see on the left half there, it's mostly all of our new orbital coverage, where we filled in pretty much all of the gaps consistently. On the right-hand side, we haven't yet marched all the way around the planet to fill that in, so it's still showing some of our flyby coverage. But what you can see there in yellow outlined is the approximate extent of a really large unit of smooth plains. And these plains are thought to be volcanic in origin. And we had some hints from the flybys. Mariner 10 actually got the best look of these plains, but now we're seeing for the first time their full extent, which is around 4 million square kilometers. It's around half the size of the continental US. And if we can go to the next graphic, you can see this is just an example of how we actually did see some of these plains during the flybys, but because we're flying by close to the equator, looking up at high latitudes is really a difficult challenge. And so orbit is perfect for that. If you can add the overlay there, you'll see this is the same area as seen from our flyby images, where we can look straight down on the surface. And so from our more detailed look at this beautiful large unit of smooth plains, we're seeing all kinds of evidence for volcanism, the tectonic deformation of these plains. In this image toward the center and on the right side there, actually you can see ghost craters, which are pre-existing impact craters that were later covered over by lava. And you can just see their rims affecting the structures there. If you can bring up the next image, please. We're also orbiting, in our orbital coverage, we're collecting color images through 8 color filters of the whole planet with a resolution of around 1 kilometer per pixel. And so the reason we image Mercury in color is so that we can try to understand its composition. The colors of the surfaces are related to the rock types that are present on the surface. And so this image is also showing the smooth plains. They're the less cratered area that shows up as kind of an orange or red in this color scheme. If you bring up the next image, or the last image, sorry, was an image where the infrared red and blue filters were in the red, green, and blue channels. This image is an enhanced color look at the same region. That just shows these smooth plains are compositionally distinct from their surroundings, and while we don't yet know their composition, that's something we're working on. But we're really excited to keep studying this huge volcanic deposit near the North Pole, its implications for the evolution of Mercury's crust and how it formed. Next slide, please. This is just showing our coverage so far that we've obtained from orbit in our monochrome mapping campaign. So you can see in just around 3 months, less than 3 months, we've filled in a great deal of the planet already, at least for this hemisphere. If you can start the movie, when we zoom in here, you can see these images are collected at an average resolution of around 250 meters per pixel. And when you zoom into the full resolution, you can start to see this is just one of the many spectacular features on Mercury. This is a 13-kilometer impact crater. And that dark region that you see to the south is impact melt, which flowed from the crater. Impact melt forms when the impact occurs. The temperatures and pressures are very high. They melt the rock on the surface, and it can flow, in this case, away from the crater. And this particular view here shows the impact melt is very dark. The color imaging and also the reflectance spectrometer on MESSENGER hint that this may be a unique composition, distinct from its surroundings, and definitely different from most of the typical impact melts that we see on Mercury. Next, please. In addition to our standard color and monochrome mapping imaging campaigns, we also are able to collect high-resolution targeted images for regions that are of high scientific interest, things that we saw during the flybys and wanted to get a better look. This is showing the crater Degas, which is around 50 kilometers in diameter. On the left-hand side, you'll see that was the coverage from Mariner 10. And so our targeted images and color here are acquiring a great new level of detail. You can see on this crater there's impact melt that covers the floor. It has these fractures that formed as the impact melt cooled and solidified and cracked. And then the beautiful bright area in the center is the central peak complex there. And the next slide, please. We're also able to acquire targeted monochrome images, and this is a great example of the importance of these high-resolution images. Messenger can acquire images at up to 10 meters per pixel. This one here is 21 meters per pixel. And it shows a region that we saw these areas during the flybys that had patchy, bright material on crater floors, sometimes in peak rings of craters. And we simply didn't have the ability to determine what they were because we couldn't see it at any higher resolution. We look at these targeted images, we can see that these patchy, bright regions are actually terrain that appears to be etched. There are clusters of small, rimless depressions, a few hundred meters to a kilometer. They often have diffuse, bright halos around them. The line on the bottom image, where you can see kind of a line of these little pits and etched terrain, that's actually the peak ring of an impact crater. And so we still aren't sure how these formed. There are a couple ideas. When you see rimless depressions like this, in other places, they're often due to an explosive volcanic eruption where you have a gas that, when it gets near the surface and the magma expands, explodes, like Mount St. Helens, for example. But these features do appear quite different from the typical vents that we see on the moon or on Mercury. They're really unlike anything we've seen before. So another idea is that they contain some kind of material or compound that is not stable when it's exposed near the surface of Mercury. So a volatile material that evaporates or sublimes when exposed at the surface. So we're really excited to keep studying these features, try and understand their origin, apply data from all of the other instruments on Messenger. And with that, I'll pass to Larry.
Thank you, Brett. I'm very happy to be here today. I'm going to talk about results we've gotten from two specific instruments on Messenger, the X-ray spectrometer and the gamma-ray and neutron spectrometer. These instruments are designed to measure the abundances of the chemical elements at the surface of Mercury. Now, the abundances of elements on planets depends on what the planets were originally made out of, their entire geological history. So they're very diagnostic of important processes. Over the years, many ideas and models have been put forward about what the composition of Mercury might be based on various formation models and evolution models. But it was only until now that Messenger is in orbit around the planet that we can actually start testing these models in detail and really see if any of them are right. And what we were finding, as Sean indicated, is that in many cases, a lot of the original ideas about Mercury are just plain wrong. And so we're finding some surprises, and we're getting very interesting results, as I'll show you. So this first animation is an illustration of how one of these instruments works, the X-ray spectrometer. Now, we use this instrument, basically X-rays from the sun are emitted by high-temperature plasma in the outer atmosphere of the sun. These X-rays hit the planet, and they can cause re-emission of fluorescent X-rays. This is very much like a black light poster glowing under a UV lamp. So it's a fluorescent process. These X-rays can be detected by the instrument on board the spacecraft and used to determine what elements are present and in what abundance. So this technique depends, as I said, on the X-rays from the sun. The solar X-ray emission varies with time wildly and gets especially high during large solar flares. Well, we've been fortunate that the sun has been relatively active since we went into orbit 3 months ago. So we've gotten some very good fluorescent X-ray data from the surface. So we're getting good measurements right now of the average composition of key elements like magnesium, aluminum, silicon, sulfur, calcium, titanium, and iron with this instrument. So as an example, may I have the next slide, please? This shows a graph of the magnesium to silicon ratio plotted against the aluminum to silicon ratio for different types of rocks on the Earth and on the Moon and on Mars. And what you can see is that these different types of rocks and planets lie in different places on this plot. And so it's a good discriminant of different processes. For example, at the bottom right, you can see that rocks from the interior of the Earth are relatively enriched in magnesium and depleted in aluminum, compared to typical rocks on the surface of the Earth, like basalts, that can be seen at the sort of middle left with higher aluminum and lower magnesium. Many rocks on the surface of the moon are even more enriched in aluminum than typical Earth rocks. So they're up in the upper left portion of this diagram. And that reflects a very high abundance of minerals, feldspar minerals. So if we go, and on this graph, we can also see that Mars occupies an entirely different region on this plot. So different planets lie in different regions, and where does Mercury lie? Well, if I have the next slide, this shows our data that we're determining from the X-ray spectrometer. The lighter symbols indicate measurements over very large areas, sort of 1 to 2,000 kilometer footprint size, whereas the darker symbols are slightly better resolved measurements down to a few hundred kilometers. And what's clear here is that Mercury is not the moon and it's not the Earth. The surface of Mercury occupies a fairly unique location on this diagram for the surfaces of terrestrial planets. It's got lower aluminum and more magnesium relative to silicon, so it has a lower abundance of feldspar, and it clearly has undergone a unique geological history. In addition to these data, the X-ray spectrometer has made two additional very interesting observations. First, we have found that the surface of Mercury has relatively low abundances of iron and titanium. Now, it's been known for many years from ground-based spectral observations of Mercury that the silicate minerals at the surface of the planet are low in iron and titanium. But data from the flybys of MESSENGER of Mercury suggested that there, in fact, could be much higher abundances of iron and titanium at the surface that just were not in silicates, were in other phases. Well, the X-ray data clearly showed this is not the case, that the rocky part of the planet is low in iron and titanium. So it helps show the power of orbital missions versus flybys, that even when you get excellent data on flybys, it's not always easy to unambiguously interpret it. So here in the orbit, we're getting this. And again, it shows that Mercury is different from the other planets, which have much more iron and titanium in their rocky portions. The other very interesting observation that we've found is that the data reveal that the surface of Mercury has a very high, relatively high sulfur abundance, on the order of a few percent by weight of the surface of Mercury appears to be sulfur, which is at least a factor of 10 times higher than the crust of the Earth or the Moon. We do not fully understand this yet, but it almost certainly relates to the origin of Mercury, that Mercury most likely formed from building blocks that were fundamentally chemically different from those that formed the Earth and Moon originally. It also has important implications for understanding volcanism. As Brett was talking about, we have evidence for explosive volcanism possibly driven by volatile gases, and on the Earth, this is often driven by sulfur-bearing volatile gases. And so the presence of sulfur should tell us new things about the nature of volcanism on Mercury. So shifting gears, I have the next animation, please. So this is an illustration of the other instrument, the gamma ray and neutron spectrometer, which probes material to depths of a few hundred or a few tens of centimeters, a few feet. And basically this instrument works when galactic cosmic rays streaming through space interact with the surface. They make neutrons. They can be fast, high energy, or slow, and then they can get slowed down to be thermal neutrons. These neutrons can interact with materials at the surface to produce gamma rays that have energies characteristic of the elements. And in addition, if you have naturally radioactive elements like potassium, thorium, and uranium, they can decay naturally and release gamma rays. And all of these neutrons and gamma rays can be detected by the instrument on board the spacecraft and used to determine the composition of the planet. I'm going to focus today on the results for potassium and thorium, both of which have radioactive isotopes, so we can detect their abundances. May I have the next slide, please? So the ratio of potassium to thorium has long been understood to be a very useful probe in planetary science. And the reason for this is potassium is a rather volatile element. So it evaporates at relatively low temperature, and thorium does not. So the ratio of these two elements can provide a great deal of information about thermal heating processes that occurred in the early solar system when these planets were coming together. So this plot shows the potassium to thorium for Venus, the Earth and Moon system, and Mars. And a striking thing on here is that the Moon has a much lower ratio of potassium to thorium than the other planets. And this is a direct reflection of the very, very high temperatures that the Moon experienced when it formed by a giant impact of a Mars-sized impactor on the Earth. And it got so hot that the potassium and other volatile elements like it essentially evaporated away. Well, prior to MESSENGER, many ideas about Mercury suggested that it should also have a low potassium to thorium ratio. Mercury formed very close to the sun in the early solar system. It was thought that the nebula from which the disk from which the solar system formed, the planets formed, was hot there, and there are many formation models for Mercury that suggested this ratio should be low. But in fact, the gamma ray results show the opposite. May I have the next slide, please? They've been able to measure this ratio on Mercury, and surprisingly, it's not low. It's, in fact, as high or higher than that of the other terrestrial planets. So this tells us right away that Mercury is not highly depleted in these kinds of volatile elements, unlike previous ideas. It rules out some formation models, and it's completely consistent with other observations, like the high abundance of sulfur, which is also a relatively volatile element, and the presence of sodium, which has been observed over the years in the exosphere around Mercury, and it's clearly been coming from the surface. So there seem to be a large amount of volatile elements in the planet. And all taken all together, these elements are changing our view of the origin of Mercury. It indicates that Mercury is not the Earth, it is not the Moon, and we're going to use these data in conjunction with all the other observations to really try and better understand how the planet formed, what it formed from, and what has happened to it in the intermediate 4.5 billion years. And with that, I will pass it on to Sean.
Thank you, Larry. I'd like to share some of our recent findings from two different investigations from the MESSENGER mission: the measurement of the topography of the surface of Mercury and the measurement of Mercury's internal magnetic field. If we could go to the first animation, you'll see a very schematic depiction of the operation of Mercury's Mercury laser altimeter that sends 8 times a second a short pulse from a powerful laser, and it records the reflection of that laser pulse off the surface. And from the time of flight of the laser signal and from precise knowledge of the position of the spacecraft, it determines a topographic profile underneath the path of the spacecraft. While we're switching to the next animation, let me say that laser altimeter has operated more than 2 million times from orbit so far. And what you see playing out on this animation are tracks color-coded by elevation of the topography of the northern hemisphere of Mercury. We're seeing the broad shape of the planet for the first time. We're seeing detailed profiles of geological features, impact craters and basins, fault scarps, volcanic terrain. You're seeing that the northern region of the planet is surprisingly low. The area of the northern plains that Brett talked about has some quite low but variable elevations, several kilometers below that for the average of the planet. The total range in elevation is as much as 9 kilometers on the basis of observations to date. One of the investigations that we're using altimetry to pursue is a 20-year-old mystery that was set by Earth-based radar observations. And the next graphic shows a modern radar image of a portion of the north polar region of Mercury obtained at the Arecibo Observatory in Puerto Rico. What you see are bright deposits at radar wavelengths that are thought, on the basis of their radar characteristics, this is a 20-year-old proposal, to be water ice, this on the planet closest to the sun. Now, that planet gets very hot at the equator in the daytime. So how can there be water ice at the poles of Mercury? The hypothesis, now going back 20 years, is that water ice resides on the floors of impact craters that are in permanent shadow, that never see sunlight, and therefore are extraordinarily cold and remain cold for millions or billions of years. Well, we are testing that idea with several of our investigations, but today let me tell you that the first test has been with altimetry. The next slide shows an example of one of these craters on one of our global mosaics. The one circled in red hosts polar deposits on its floors. You see the radar map superimposed on the global mosaic from MESSENGER. And our altimeter made several passes over this particular crater, 25 kilometers in diameter, 15 miles across, early in the orbital phase of our mission. And the next slide shows a contour map of that crater built up by the topographic profiles that we collected from orbit. And this contour map, combined with calculations of where the sun shines as a function of time of year and position on Mercury's surface, allows us to test what parts of the floor of this crater and other craters at high northern latitudes are in permanent shadow. And indeed, this crater passes the test. The portion of the floor that is in permanent shadow coincides with the portion of the floor of the crater where we see the radar bright deposits hypothesized to be water ice. So stay tuned. This is a very exciting hypothesis now with us for 20 years that planet Mercury may have large quantities of ices at the North and South Pole. The very first scientific test of that hypothesis using messenger data from orbit has passed with flying colors, and we look forward to results, particularly from our geochemical remote sensing instruments, the neutron spectrometer in particular. Given enough time from orbit, and 1 year we've shown is enough time, so stay tuned, we'll demonstrate whether or not the material at the poles is likely to be water ice on the basis of excess hydrogen. Let me turn now to the magnetic field of Mercury. The magnetic field was discovered by Mariner 10. It's much smaller than the magnetic field of the Earth. You probably know that Venus and Mars do not have a magnetic field, so Mercury is the only other Earth-like planet to have one. And what we thought on the basis of the flybys was that Mercury was a miniature version of Earth's magnetic field, produced by similar processes and with broadly similar geometry. Now that we're in orbit, we can measure that magnetic field every day. And what we're seeing is that it is not a miniature of the Earth's field. Before you start the animation, let me say what you're going to see. We're looking down on the North Pole of Mercury. Every orbit, we determine the position of the magnetic equator, the part of the orbit where we cross Mercury's magnetic equator, defined as the point at which the internal magnetic field is parallel to the spin axis of the planet. And those red dots are the location of the magnetic equator looking down from the North Pole. So all looks well. But now if we can start the animation, you'll see where that magnetic equator lies. It is not at the geographic equator of the planet, which is that gray line. It is north of, systematically north, on every orbit, north of the geographic equator by 2/10 of a planet radius. What that means is that the magnetic field in the northern hemisphere is stronger and differs from that in the southern hemisphere. And it means that the process that creates the magnetic field, which we think is somewhat similar to that in Earth, that it arises from dynamo processes in the planet's core, must be capable of producing this asymmetry between the north and the south. Now, there are some consequences of having this strongly asymmetric field, and one of them is depicted on the next slide. If you map the magnetic field lines at the north and south polar regions of Mercury, those magnetic field lines look pretty complicated, but focus on what is different between the north and the south, the north on the left and the south on the right. And what is different is the area around the pole itself, the areas with the letters N and S. And the next slide shows those in more detail. Those areas are called polar caps for students of the magnetosphere, and they're areas where the field lines don't close around the planet, but are open to interplanetary space. Why is that important? It is important because open field lines are like interstate highways for charged particles from the interplanetary environment. And those charged particles come roaring in and hit the surface of Mercury. What happens when they do? One of the things is that material is kicked off the surface and contributes to Mercury's very tenuous atmosphere called an exosphere. And another is that the impacts of these charged particles change slowly over time, that the chemistry and the color and the reflective properties of the surface by a set of processes known as space weathering. So a prediction of this new model for Mercury's magnetic field is that the processes of generation of the exosphere and the processes of changing the color and reflectance of Mercury's surface should be very different near the North Pole and near the South Pole. And we'll be testing these ideas as we go forward. But Mercury's magnetic field environment, Mercury's magnetosphere, is different in some other ways as well. And I will turn the podium now to my colleague Ralph McNutt to describe some other new results.
Thank you, Sean. What I'd like to do is to amplify on some of the things that Sean is talking about the magnetosphere, and also talk a little bit about a rather serendipitous discovery that was made with the instruments that Larry was talking about for doing our geochemistry observations. And if I could have the first graphic, please. Larry was talking about using our gamma ray spectrometer to look for gamma rays from the surface of the planet. And this is actually what the gamma ray spectrometer on Messenger looks like in schematic. The yellow part at the top actually points back toward the surface of the planet. That's nominally where the gamma rays come in through. And the blow-up shows the working piece of this. The red area is actually a single polished crystal of germanium, the semiconductor, about 2.5 inches by 2.5 inches, and that's what we use for actually looking at the gamma rays. But it turns out that at energies that are lower than what we use for looking at the gamma rays, there is still some response of the instrument to what is also going on nearby to the spacecraft. And if I could have the next graphic, please. Around the spacecraft in the magnetosphere, we know that there are charged particles of plasma. One of the things that, of course, has been a big mystery is that at the time of the Mariner 10 flyby, the first one back in 1974, not only was the magnetic field in the magnetosphere discovered, but there were also these bursts of energetic electrons. And this is something that we haven't seen on any of the flybys that we've had with Messenger going by the planet. And we have a detector that's on board, the energetic particle spectrometer, specifically for looking for events like that. And it's been quite silent during all the flybys we had. But then something interesting happened once that we finally got into orbit. And this just illustrates one of the things that can happen in particular with the gamma ray spectrometer that's got a very large active area that allows you to see things that you can't necessarily see with the other instruments. We've of course got, there's a possibility of having electrons near the spacecraft. Those are indicated on the left. And those can come in and actually hit the outer case of the instrument. And if I could go to the next graphic, they're not energetic enough necessarily to go through that case, but what does happen and what can happen is I can actually make X-rays internal to the instrument itself. And it's exactly the same physical process that's used in medical X-ray imaging equipment. It's exactly the same process that happens in the upper atmosphere of the corona of the sun, where that hard X-ray fluxes are emanated from, such as have happened here in the last couple of weeks. And so one of the possibilities we actually have with this instrument is not only in looking at the gamma rays coming back from the surface, but actually being able to see gamma rays that are being produced within the instrument housing itself if there are enough electrons in the region of space that we're flying through. Certainly the kind of usage of this instrument that it was not designed for, but again, it gets back to serendipity, having a happy discovery based upon something one wasn't expecting. And if I could go to the next graphic, please. And let me just explain this for a minute. This is very similar to what Sean was just showing you with the where the magnetic equator lines up on the planet. In this case, again, we're looking down on Mercury from the top, from the North Pole. But in this case, what we're looking at, the greens and the arrow regions, are the pieces of the orbits that are basically we've painted with the areas where we've seen these energetic electrons. And it's not a question of just simply flying through the area and having the electron flux come up. We see this as bursts. Sometimes they're only tens of seconds long. Sometimes they last for several minutes. They're sporadic, but they happen like clockwork almost on every orbit. A lot of variations. And the other thing it's important to note from this graphic as I look down on this isn't a coordinate system where that the sun is off on the right-hand side. And where we're seeing these are located all around the planet. And if we could go ahead and roll this as a film clip, this shows why that we didn't see them during the flybys. They're all in the northern hemisphere. Sort of the darkish gray areas or the lightish gray areas on here are pieces of the orbits that Messenger was in, has been in since we've gotten into orbit around the planet. And you can see the distribution of these things tends to be at mid-northern latitudes. The blue ones, which tend to be more symmetric about the planet, are at higher energies from the gamma ray detector. The lower energy ones are from similar physical processes. that we're seeing in the X-ray detector. Again, it's the same two instruments that Larry was talking about in a region of the measurement chain where that there's no interference with what we're looking for with the geochemistry, and nonetheless that we're able to get an idea of what's going on around the planet. And it turns out, of course, that with the 3 MESSENGER flybys, those were all near the equatorial plane, where we don't see any of these events. The Mariner 10 flyby back in 1974 was at high northern latitudes, and again, these events for all the world look exactly like what was seen on Mariner 10. So the reason we didn't see them on MESSENGER is simply because we were going through the wrong part of the planet's magnetosphere. And if I could go to the last graphic, this is an attempt to sort of put all of this in context. Again, the sun is sitting off on the right-hand side, and this is a schematic that's showing a selection of some of the magnetic field lines. The solar wind blows outward from the sun and tends to compress the magnetosphere on the sunward side of the planet, and there's a so-called magnetotail where the field lines are drawn out on the other side. You can see the magnetic equator here in this schematic. We've displaced it northward. Again, this gets back to what Sean was illustrating about the difference in this magnetic field from that of the Earth. And again, the green areas are where we've seen the X-ray, where the X-ray detector has lit up with lower energy emissions from electrons that have characteristic energies of maybe 5 to 10 kiloelectron volts. And the blue regions are where the gamma ray spectrometer has lit up with electrons due to electrons that are at higher energies. One of the original ideas was that if indeed there were energetic particles, that they would tend to be concentrated in the night side of the planet's magnetosphere, but that's not what we're seeing. We really are seeing them all around the planet. And this is really different, again, from the sorts of things that we've typically seen in the Earth. In the Earth's magnetosphere, there was a lot of work back after the Mariner 10 flyby, speculation on how that Mercury and the Earth's magnetosphere might be similar. But once again, as with some of these other observations, such as with the geochemistry of the planet, we're finding out that Mercury really is a world in and of its own. And we're finding that just like the Earth, it's got its own personality. Mercury is one of the terrestrial planets, and therefore provides some context for what was going on in the inner part of the solar system back when the planets were condensing from the solar nebula. But as we look, and as we continue to look with MESSENGER at Mercury, looking close up with targeted observations, using all of the various instrumentation, such as things that were simply not available with the technology at the time of Mariner 10, we're managing to really explore a new world for the first time. We are out there on the edge. We're doing things with technology that had to be developed for this mission. And we're learning things by being in a place that no human being has ever, by proxy, gone before. And that's what science and exploration and the sorts of things that come out of the Science Mission Directorate at NASA are all about. And I think all of us are very pleased to be part of MESSENGER as one of these discovery missions which has now gone through only 1/4 of its nominal mission at Mercury, and there's a lot more to come, and all I can say is keep following us. The best is yet to be. And Dwayne?
Thank you all, and congratulations again. Just a reminder to our television audience, all of the images that were presented today and much, much more is on www.nasa.gov/messenger. Now, I kind of snuck in my introductory remarks a little surprise of our own here. You heard about the surprises of Mercury, but headquarters has a surprise. So before we open it up for questions, I would like Dr. Jim Green, the director of NASA's Planetary Science Division, to come to the stage.
Thank you, Dwayne. And Sean, will you please come here?
Thank you, Jim.
On behalf of NASA and the U.S. Postal Service, it's my great pleasure to give you a commemorative first aid cover. It's everything Mercury that NASA's been doing.
For 50 years.
For 50 years. And as you know, with the stamps that have been issued, it's forever. They're forever stamps, and it's forever Mercury. And as Ralph said, more great science is yet to be coming with the rest of the mission. So congratulations to you and the team.
Thank you, Jim.
achieving
Thank you.
the first that you have and getting Messenger into orbit.
All right, thank you very much.
Okay, let's see if we have any questions here. We're going to start here at NASA headquarters. Wait for the mic. Give your name and affiliation.
Randy Shostak, reporter with EOS, newspaper of the American Geophysical Union. This is very exciting information. Thank you for the press conference. I wondered if you could elaborate, particularly on some of the latter comments by Dr. McNutt, and if you can put this in broader context for me. What does all this add up to? What do all these new images, what do all these new findings add up to? And at this point, what are you most pleased about to date, and what are the surprises and things that puzzle you the most?
Well, I think that certainly the thing that we're most pleased about is that we're in orbit. We've got a healthy spacecraft. We've gotten through the hottest part of the orbit, and everything is still working. I've personally been involved in a variety of NASA missions, and all I can say is that I keep being amazed every morning that I get up how well that Messenger is going. It has been a tremendous partnership between the Messenger team and NASA, actually, again, pulling something off that no one has ever done before. I think in terms of what we're learning, again, one of the things that we said when we started the mission in the beginning is that Mercury is that end member planet of the terrestrial planets. It tells us something about the inner part of the solar nebula. It tells us something about how the terrestrial planets formed ultimately. Again, the sorts of results that Larry was discussing about how that the potassium to thorium ratio differs amongst the planets, and that Mercury has really been a surprise there. It's certainly clear from that, as well as from the images that Brett was showing, that comments to the contrary, Mercury ain't the moon. There have been a lot of comments that one would read saying how that, well, it just looks like another dead piece of rock like the moon. Why are we doing this? And the reason we're doing it is because you learn something by going to places that we haven't been before. I mean, the solar system is our home. We're here. We know that. We don't know as much as we might like to about our origins and about kind of where how all of this came together. And by going back and taking a look in detail at places like Mercury, we're able to put more of those jigsaw puzzle pieces together. Again, Sean is talking about the fact that we've got this very interesting magnetic field configuration. The only other place in the solar system where that you have something like this is the magnetic field of Saturn, where that the spin axis and the dipole axis are aligned, and it turns out that the magnetic equator of Saturn is displaced northward of its geographic equator, not by as large a percentage, something like about, I think it's like 0.06 Saturn radii as compared to about 0.2 Mercury radii for Mercury, and certainly the environment and the chemistry and the geophysics of Mercury and Saturn are quite different. And yet now we have examples of two active planetary dynamos in the solar system that shouldn't be there. And for a long time, I know with the investigators at first really at Pioneer 11, and then with Voyager, and now of course with Cassini, there's been a lot of speculation about whether that Saturn was just sort of the odd man out. Well, now with these messenger observations, we've been able to show that no, it's just an example. It's one of two. I think that one of the other really surprising things and very interesting things is, again, this example of how much flooded area of pyroclastic flows, these explosive flows of volcanism early in the history of the planet that there are. And of course, one of the things we've remarked upon before are the so-called lobate scarps, where that we see this evidence of Mercury having shrunk with the crust folding over. Where of course Sean's been talking about the idea about the ice and the craters, and the fact that we have this LIDAR this laser altimeter that's now in orbit around Mercury, where that we can make these deductions about the overall topography of the planet. I mean, this is just incredible. There's a lot more to come. So I don't think it's so much a question of what is the most amazing, but really the question of what about the mission and the results to date have not been amazing, because this really is the undiscovered country, and we really are, for the first time, exploring a new world.
You have a question? You pass the mic and there. And name and affiliation, please.
Hi, Ann Walters with the German Press Agency. You mentioned quite a number of observations that you've had that weren't what you were expecting to see, and I was hoping that you could maybe say what was the biggest misconception that there was about Mercury before you started this mission.
The biggest misconception. The biggest misconception was that we would go to a planet orbited for the first time and not be surprised. and some, even in the planetary community, after the Mariner 10 mission, placed a low priority on returning a spacecraft to Mercury on the grounds that it was very much like the moon. We had been to the moon. It was an example, to use a phrase coined by a very famous space scientist, one of the burnt out cinders of the solar system. And it is anything but that. Just to elaborate very briefly on the eloquent summary that Ralph gave, and give a little more context, NASA is doing some other wonderful missions that are expanding at a huge rate our knowledge of planets around other stars. You know, Kepler has announced, tripled the number of extrasolar planets recently in their announcements. And many of those planets are at distances similar to that of Mercury from our sun. Many are a growing number are of masses that are approaching that of Earth and Venus. But we have in our solar system 4 experiments in how Earth-like planets evolve once they form under slightly different conditions. Different distance from the host star, different mass, different starting composition. What we're learning is that each of those experiments had an extraordinarily different outcome. And one of those experiments we live on. So it really behooves us to understand in a very general way how Earth-like planets form and evolve and operate. And what Mercury is telling us is we didn't understand in complete generality how planets of the Earth-like class operate in detail. So we're learning new things every day.
Okay, now we will switch over and go down to the Kennedy Space Center, where I believe we have a question. Kennedy?
Hello, Ken Kramer from Spaceflight Magazine. For anybody, please. You talked about the water ice at the North Pole. I'm wondering about how much of the surface do you think would be covered with this water ice? Is the fact that it was depressed about 9 kilometers, I think you mentioned, does that increase or decrease the chances of finding water ice? And is the LRO data with a similar instrument, are you comparing results there, and has that been helpful in interpreting your data at all? Thanks.
Ken, let me take that question. This is Sean Solomon. In parts, the area of polar deposits has been well worked out by the Earth-based radar folks. That area is quite a bit larger than on the moon. We don't know the thickness of those deposits. We know that it's thick enough to have radar bright characteristics for radar of different wavelengths, which means it's at least several radar thicknesses in extent and the vertical direction, meaning meters or more. There is a beautiful laser altimeter on the Lunar Reconnaissance Orbiter known as LOLA, and that is producing data at a huge rate. And the topographic maps that the Lunar Reconnaissance Orbiter is creating from the LOLA data is just exquisite in its detail, and is indeed helping to define, as are images taken from the same spacecraft, areas of permanent shadow. And as you know, NASA has flown other missions, like the LCROSS mission that impacted into one of the south polar craters thought to have water and other volatiles, and showed quite spectacularly on the basis of spectral evidence from the ejecta that there is water there. But if water is the major constituent of the polar deposits on Mercury, then we have the irony that the planet closest to the sun is going to have more ice at its poles than even our own moon. And so stay tuned. As this mission evolves, we'll be relying more and more on the geochemical remote sensing instruments, which take time to build up their observations. But the neutron spectrometer, the gamma ray spectrometer, have the ability to tell us what those materials are. Is it water ice? Is it something else? And we expect to have that answer before our mission is done.
Okay, now we can go to the phone line, and we'll take first Lisa Grossman from Wired.com. Go ahead, Lisa.
Mentioned that the data from the spectrometer is ruling out some models of what Mercury's composition can be. What models are those, and what ones are left over?
You want us to repeat that? Lisa, could you repeat the full question again? I'm sorry.
Sure, sorry about that. I was wondering what the models of Mercury's composition and formation have been ruled out already by the composition data you're getting from the spectrometers, and what possible models are still left.
So this is Larry Nittler. I'll take that question, Lisa. There's a number of models of the formation of Mercury that were proposed after the Mariner 10 observations in the 1970s indicated it had an unusually large core. And one of these models was that the planet formed at normally or similarly to the Earth and had a normal size core, meaning Earth-size core relative to the radius of the planet. And then because the sun went through a phase of extreme high intensity in its earliest stages, essentially Mercury was so close to this hot sun that the outer layers could have evaporated off. And in this model, this would have predicted very, very low abundances of things like potassium and sulfur and sodium. So we can rule out this kind of model. There are other models that propose that Mercury formed from a specific kind of meteorite called a CB chondrite that are very, very rich in metal. Now, these models make very specific predictions for the composition of lavas and rocks at the surface of the planet. And for the most part, these are not in detail, not in agreement with our observations. So these models in detail can be ruled out, but possibly variations on them will eventually be proven to be right. Another model is that Mercury formed larger and similarly to the Earth, and after it had formed an Earth or Moon-like crust, another planet hit it and smashed off the outer crust and part of the mantle, leaving a residual mantle that could have then produced a new crust. At this stage, we cannot rule out this model. The data, some of our compositional data are certainly consistent with this idea in broad outlines. Whether the high sulfur abundance is consistent with this, we have not yet figured out. But this is a model that's still in the running. And there are probably going to be many more models devised before we have an answer on this as we continue to get interesting data. But thank you.
Our next question will be from Peter Spotts.
Hey, thank you.
Thanks, Lisa. Our next question will be Peter Spotts from the Christian Science Monitor.
With the Christian Science Monitor, and actually that pretty much was my. Can you hear me?
Yes, sir. Go ahead, Pete.
Am I getting through?
Yes.
I guess so. Okay. That actually answered most of my question, but let me just throw one other one related to that. And is there any possibility for a migration of Mercury from forming in a bit more distant location in the solar nebula and somehow migrating in?
I can take that, Pete. This is Sean Solomon. The process, I think you know, or you wouldn't have asked this question, of building up the inner planets is one with a lot of chance encounters. We would call it stochastic, that the interaction of growing objects that start out many and become few is not fully predictable. and depends on particular encounters that can result in growth of a larger object or disruption of an object. And some of those simulations that have been done of the growth of the inner planets do include the possibility that Mercury started to form at a different place in in solar distance than it ended up. My late colleague George Wetherill did some of the pioneering calculations of that sort. That said, there are also interesting studies of the migration of planets once formed, and this work was really stimulated by the discovery of extrasolar planets near their host stars, and a lot of the attention has been directed at the major planets whose migrations may have had a big influence on the history of small objects in the solar system. But there's a very interesting study by a French dynamicist of the long-term evolution of planet Mercury. And their simulations have shown that some of the orbital characteristics of Mercury, like the large eccentricity of the orbit, like the large inclination that Mercury's orbit makes with the orbits of most of the other planets, are not fixed in time, but evolve. And they made a very interesting prediction in a paper in Nature a couple of years ago that 3.5 billion years from now, it's not something we have to worry about next week, that there's a possibility that the orbit of Mercury will substantially disrupt the orbit of one of the other inner planets. And so it's something that our great-great-great-great-great-great-grandchildren might devote some time to thinking about, that Mercury and its orbital evolution may have major consequences for the orbit of our own planet. But that's a prediction that may or may not be borne out according to an article in Nature. But I can send you that link if you're interested, Pete.
Okay, next up is Kelly Beatty, Sky and Telescope Magazine. Kelly?
But is it possible? Oh, go ahead. Go ahead.
Yeah,
Thanks.
Pete, we'll give you an opportunity to do follow-ups because we're approaching the top of the hour. So let's go ahead and go to Kelly Beatty at Sky and Telescope Magazine.
Thanks very much. I came in a little bit late, so Sean, if you covered the possible interior structure of the planet, I missed it. But if I didn't, can you say anything about the interior structure of the planet, and in particular, what an offset magnetic field says about the state of the core?
Okay. Kelly, you didn't miss much on that topic, and we didn't cover it at great length. We know on the basis of measurements made with Earth-based radar that the outer core of Mercury is molten, like the outer core of the Earth, molten, metallic, iron-rich. We also know the approximate radius of the core just on the basis of the mean density of the planet. That's been known for 50, 60 years. And it's at least 3/4 of the radius of Mercury. What the asymmetry, the equatorial, the asymmetry about the equator of the magnetic field means has still to be sorted out by the theorists. But one possibility is that the field-generating region of the outer core, or in particular the boundary between the outer core and the mantle, may be strongly different in the northern hemisphere and the southern hemisphere. This idea has been put forward as an explanation for an early magnetic field on Mars that is much stronger in the southern hemisphere of Mars than in the northern hemisphere, to explain the strong magnetic anomalies recorded in crustal rocks on Mars and their locations, which are dominantly in the southern hemisphere. So I have no doubt that our new results on Mercury's magnetic field geometry is going to stimulate a variety of new ideas for how Mercury's magnetic field is generated, how that field might vary with time, how it varies with position, and I look forward to those models and to our ability to test them.
Okay, folks, we are going to have to wrap up here at the top of the hour. For the media who are still on the line, please get in touch with my office or APL Public Affairs to get some follow-up questions and interviews set up for later in the day. I want to thank you all for showing up and joining us today. Congratulations to the Messenger team. Again, go to www.nasa.gov nasa.gov/messenger. Science never sleeps.